In the previous lecture, we started with frequency response. It was the first introduction of frequency response. How do you do frequency response evaluation in circuits? And we learned a few tricks to quickly do a hand calculation of frequency response. In this lecture, we are going to dig in deeper and we are going to understand how do we evaluate each device in terms of frequency response. We will go through bipolar transistor, a Mosfet transistor, and then we will look at all the capacitances which are contributing to frequency response in each device. And then we will also learn one particular term that's called FT, which is a transition frequency or a transit frequency for each device. This frequency kind of shows you what's the maximum limitation of each device in terms of frequency range of operation. First, we will look at bipolar transistor high frequency model. If you remember, when we looked at bipolar transistor, let's take an example of an NPN transistor. We have three layers. One is N, P, and N. The top layer I'm showing in this particular example is collector. The center sandwich layer is the base, and the bottom layer is the emitter layer. And we draw this as, for this transistor to be in active region, the collector base junction is reverse biased. So we will show that as some dotted line here, which is showing the depletion layer. Base to emitter junction is forward biased. That's the basic definition of our active region. So we will have some, I'm showing it in green like this. When we studied this earlier, we just looked at a DC model. We did not have any capacitive components in here, and the DC model looked like this. We have a resistor called R pi. Right. Across R pi there is a voltage V pi. This is our emitter, and we have output resistance, which is connecting between collector and emitter, and this is our base region. Base to collector junction is reverse bias, and that will give us a capacitance called C mu, which is a reverse bias junction depletion capacitance, and it's shown in this fashion. And base to emitter is forward bias. That will give us a capacitance C pi between base and emitter junction. We are going to figure out what the values of C mu and C pi are. C mu So this is the expression for collector base reverse bias junction depletion capacitor. So C mu 0, this value is value of C mu when VCB is equal to 0. VCB is the reverse bias magnitude, and VOC is called built-in potential, and this is approximately 0.75 volts, and M is grading coefficient, and this value is approximately 0.2 to 0.5. All these are coming from device physics. We are just going to use the final result. Review this again. If VCB, this term right here, is 0, then C mu will be equal to C mu 0. And if VCB collector base junction reverse bias keeps increasing, then C mu will start decreasing, because the number in the denominator will start increasing and C mu will start decreasing. And that kind of makes sense, because depletion region will get larger and larger, as a result of which the capacitance C mu will start dropping. The next capacitance that we have to be worried about is C pi. Let's see what C pi consists of. C pi is given by C diff, diffusion, and C junction. So diffusion capacitance, this particular capacitance, comes from when you turn on a BJT or turn it off. It takes certain amount of time for the charges to accumulate or escape away from the base region. That is what will give you C diffusion. And for NPN transistor, Qn is given by tau f times IC. Tau f is the forward transit time, forward base transit time. Intuitively, it's the travel time of electrons to go through the base, which is kind of in the range of maybe somewhere in the picoseconds, 10 to 100 picosecond type of range. Now diffusion capacitance, C diff, is given by del Qn by del VBE, and that is given by here tau f dic by dVBE. And we already know what this parameter is. That is our GM. So tau f times GM is our diffusion capacitance. GM we already know for bipolar transistor is IC divided by VT. The junction capacitance right here, that is the similar to C mu junction capacitance. This junction capacitance is between base to emitter junction, and that is given by C junction. In this case, as compared to collector base, the base emitter junction is forward biased, and the value of the junction capacitance is given by approximately 2 times Cj BeO, which is when VBE is equal to 0, whatever the junction capacitance is, double of that. You can relate with this to C mu 0, which is again when VCB is equal to 0, you get junction capacitance between collector and base. Similarly here, this is CjBe 0. When base to emitter junction voltage is equal to 0, then that's the capacitance. And when the junction is forward biased, this capacitance value almost doubles because the depletion region gets really, really small and narrow. So this is for the forward bias junction. And generally, the value of C mu is much, much less than C pi. So C pi is probably in the range of 1 to 10 picofarads, and C mu would be fraction of picofarad. One side note here that we have ignored, and I wanted to bring it to your attention, is that this bipolar transistor is not up in thin air. It's housed inside a substrate, right? So let's draw the cross section of a bipolar transistor. You can refer to the cross section of the transistor we learned in, I think, first or second lecture. So this is our emitter junction, which is in yellow. The base junction is in red, and the collector junction, the collector is going to be in green. So this is our collector, and red is our base. So this is the way the bipolar transistor would look like when you take a cross section. However, this entire collector, as I said, it's not up in the air. It's inside, housed inside a substrate. And this substrate is another connection, which is this substrate. Since collector is n-type, the substrate is P minus. So we will also have a capacitance going from collector to the substrate. So we have to draw this out as CCS. Generally, when you do circuit simulation, all these values are built into your model. You may have heard the simulator called SPICE, and SPICE has models of your bipolar transistors, and they will have all these capacitances and a lot more refinements included in the model. So you have to make sure that you understand that there is this CCS built into the model when you're simulating. Now we will look at MOS high frequency model. To understand MOS high frequency model, let's first draw the cross section of the Mosfet. Now this is something that all of you, I've been telling you, you need to be able to draw this cross section on your own. And this is an important part of learning. So please draw the cross section. So this is the way the Mosfet cross section looks like in 3D. Now let's draw the symbol for the device, and then we will try to infer from that which capacitance goes from where. What I have shown here is capacitance from each port to another port over here, all possible combination. And we'll go through each one of them and figure out the values for each component. For example, in this particular case, you can see CGD is the value of capacitance from gate to drain. Similarly, CGS would be the value of the capacitance from gate to source, and so on like that. Now, one thing I've shown here in the 3D picture is something called LD. LD is the overlap between source region and the gate region. So we know there are three regions of operations, and we will look at each one of them. So for example, when the device is off, when is the device off? When VGS is less than VT. So in that case, the gate to drain and gate to source, CGD, is equal to CGS, and that is given by C overlap times the width of the device. The width of the device here in this particular case, I'm going to show it in yellow so you get the point. So this is the width of the device. Horizontal dimension is the length of the device, length of the gate. Now C overlap is given by LD times C aux. So when the device is off, there is no channel under the gate. You will get gate to source or gate to overlap capacitance time W. Overlap capacitance value is LD times C aux. In this case, the C gate to bulk is going to be given by C aux. This is the oxide capacitance along with the area of the transistor, W times L, and that will be in series with depletion capacitance of substrate. And that C depletion is given by W times L and square root of Q epsilon SI and sub divided by 4/5. You don't have to remember these, but you should know that that's what is going on. Now, when the device is in triode region or the linear region, let's see what happens. When the device is in triode region, we are going to get channel under the gate. And then we say that the capacitance from gate to source and gate to drain is equal. And we allocate this capacitance to channel half and half to either side. CGD is equal to CGS, which is given by WL C aux divided by 2 plus W times C overlap, and that is given by LD times C aux. Since the channel is existing in between, is kind of like a shield, the gate to bulk capacitance is equal to 0, because now we have a channel which is connected between source and drain. So the gate only can have capacitance to this channel. So for calculation purposes, you can say that the gate to bulk capacitance is 0 in this particular case. Now comes the most interesting part, where we use the transistor most of the times. When device is in saturation region, what happens? So when device is in saturation region, then there is a channel formed, and that looks something like this, if you remember. And there is a pinch-off region at the drain, and the channel profile looks something like this. So the channel is completely associated with the source. So we say that CGD now becomes C overlap times W, and CGS is equal to 2/3 W times L times C aux plus W times C overlap. This 2/3 factor comes in because of the integration of capacitance of each segment. There is a little bit of math behind it, which we don't have to go through right now. You just have to right now assume this value, 2/3 W L C aux. The C gate to bulk is equal to 0 because channel is right there, shielding the substrate from the gate. So gate has all the lines, field lines going to the source, maximum line. Graphically, we can show the capacitance as function of gate to source voltage or the region of operation as follows. On the x-axis, I have VGS changing from 0 all the way to VGS. So when VGS is below VTH, the transistor will be off. When the VGS is between VTH and VD plus VTH, then the transistor is in saturation region. And then if the VGS increases beyond the VD plus VTH value, then the transistor will be in a linear region. So first we will plot the gate to drain capacitance, and it's going to look like this. all the way over here. From here over here, it will go up like this. And the gate to source capacitance will something like this. And again, it will come back over here. This is going to be your W times C overlap. And the green is CGD. And red is CGS. In the saturation region, the CGS is going to be 2 divided by 3 WLCox plus W times C overlap. And in the linear region, the transistor has gate to source and gate to drain capacitance, which are identical, which are half and half. So WL divided by 2 times Cox plus WC overlap. So this takes care of the gate to drain, gate to source, and gate to bulk capacitance so far. If you look at either drain or source region, then it looks like this in 3 dimension. So it's going to look like a candy bar. I like to call it like an inverted candy bar, and it's in the substrate region. If you look at this candy bar region, which is either for drain or source, then there are 2 capacitances which come into play. One is called bottom wall capacitance, and the other one is called side wall capacitance. And they pretty much mean what the words are saying. So the side wall capacitance will require some calculation of perimeter of the device, and the bottom wall capacitance will be the area of the bottom wall. That would be important. So let's write the expression, and this is again for your information, so understand where all these names are coming from. So this is your bottom wall, and this is the side wall. I'll give you expressions for both of these just for your understanding, and we'll define the terms. So C drain to bulk, for example, is given by Cj times area of drain divided by 1 plus VDB divided by PB to the power m of j. Okay. So Cj is the source and drain bottom plate junction capacitance per unit area. Hence, we multiply it with the area of the source or area of the drain. VDB is the drain to bulk voltage. PB is the junction built-in potential, which is somewhere 0.6 to 0.8 volts. And MJ or MJSW, these are unitless exponents, order of 0.3 to 0.4. And CJSW, here is the junction side wall capacitance. And all these numbers, they come from characterization of devices in a particular process. So this is how do you model the transistor with a whole bunch of different types of capacitances and the insight about where they are coming from. What we have to know as circuit designers is we should be able to figure out which capacitances to keep and which capacitances to ignore. And that's the insight I'm going to teach you, because otherwise the circuit looks very complicated. For example, if we had to, for every transistor that we are trying to evaluate, if we had to consider capacitance from every node to every node, then to do hand calculations will be a nightmare for us. So our job is to figure out which capacitances are important and only keep those capacitances in our analysis. So for saturated Mosfet, the model of the transistor will look like this. So we have, this is our gate region, and the DC model looks like this, right? So this is VGS. This is the current source is GM times VGS, and we have Rout, which is the output resistance of the transistor. Now for saturated device, what we would say is the gate to drain capacitance. If you remember, we worked on Miller capacitance. So for that, this CGD is going to be important whenever we have a gain stage. And also we have gate to source capacitance, which is CGS. And if we show bulk as a separate terminal, then there will be a drain to bulk capacitance, and then there will be a source to bulk capacitance. And these are the ones we just discussed a few minutes ago, the candy bar capacitance. Next thing we're going to talk about is FT, which is called transit frequency or transition frequency. for any device. We'll start with a bipolar device. So Ft is measure of intrinsic speed of the transistor, is defined as the frequency at which the small signal current gain of the device falls to unity. So small signal current gain equal to 1. That's when we define Ft. So let's derive this for a bipolar transistor. So what we are looking for is I out divided by I in equal to 1. Now how do we figure this out? In this particular schematic, I'm not showing the biasing circuits. The assumption is that the transistor is biased in forward active region. So draw the small signal model of the transistor Q1 in forward active region along with the capacitances that we took into account. And then we will figure out what the Ft of this transistor is. I will just write few values, C pi, R pi, and this is your GM, V pi, plus minus V pi, R out, and CCS. So there are 3 new capacitances we added. So here we can do KCL, KVL, and figure out what the value of current gain I out divided by I in is. What I would like you to do as a practice is do it on your own. What we are trying to figure out is finally expression for I out divided by I in. It will look a little bit tedious, but it's not that bad. And it's important that you go through some practice on your own. So you can pause the video right here and do the analysis by yourself. So let me explain the equations. If you remember what I taught you earlier as a way to simplify your analysis is use G's rather than R's when you have impedances in parallel. So for example, if you look over here, you will see there is a R pi and C pi, they are in parallel. So instead of drawing a parallel combination of the two, I can just add G pi and SC pi together over here. These are the equations based on KCL, KVL. They should be fairly straightforward for you to derive. Let's look at the final equation. And here we have GMR pi, that is the gain of this stage, the current gain stage. And we have a 0 at location GM divided by C mu. And since there is a negative sign, it is a right of plane 0. And we have a pole on the denominator which is at a frequency which is reciprocal of R pi multiplied by C pi plus C mu. Now what we are saying is from this slightly complex expression we can say the following. First of all, and this is where my job is to teach you how to weed out complexity from your equations to simplify things so that it makes sense. Okay. So one thing, as I have told you earlier, we say that C pi is much greater than C mu. So in this particular case, GM divided by C mu is going to be very high frequency. The right of plane 0 is at a very high frequency. Okay. So for a Ft calculation, we have to only worry about this denominator part. Okay, for Ft calculation, because this is coming into play at a very high frequency. Let's say that at S equal to omega t, we reach our Ft point. So in that case, we're going to equate this entire expression equal to 1 for Ft calculation. So then we can write Gm R pi square divided by 1 plus omega t square R pi square C pi plus C mu square is equal to 1. Now what is GM R pi? We already know this is beta. GM R pi is equal to beta. So the expression will become beta square is equal to 1 plus omega t square r pi square c pi plus c mu square. Since we have beta square on one side, we can ignore this one. For example, beta is 100, which means beta square is equal to 10,000. So we can ignore the one part to simplify our expression. And then we can get omega t is equal to beta divided by r pi divided by c mu plus c pi, which is equal to gm divided by c mu plus c pi. So this is an interesting result. For a bipolar transistor, the useful range of the bipolar transistor is going to be below this value, which is called the Ft. Now we can simplify this slightly further. As I said earlier, C pi plus C mu. C pi is the diffusion and C mu was the reverse bias, depletion. And we already said that, hey, we can ignore this C mu compared to C pi. So this will look like C pi, and then we already said that that is equal to tau f times Gm. So we can also come down is omega t is equal to 1 divided by tau f. And that's the reason it's called transit frequency. So modern bipolar process, your Ft for the bipolar transistor can be between 200 to 300 gigahertz. Ft is an indicator of frequency beyond which the transistor cannot be used efficiently, because the capacitances within the device will start mattering and dominating your frequency response. So as far as possible, we would like the transistor to behave as ideal as possible and our performance be not limited by the transistor. So this Ft limit kind of gives you that number. We can do something similar for our Mosfet. And let me do that for you. So the transit frequency for Mosfet is given by, we can do the exact same analysis. For example, again, this is a small signal analysis, and this is our transistor M1. Now, if I draw small signal analysis, including the capacitances of the device, it's going to look like this. So we can go through the similar derivation using this, and you will find out that the transit frequency is equal to Gm divided by CGS plus CGD. Very similar to bipolar derivation. Now let's step forward a little bit. What is the value of Gm? Gm is given by mu n C aux W by L times VGS minus VTH. CGS is much greater than CGD. The reason for that is gate to drain during saturation region is consisting of only overlap capacitance, whereas the entire channel, the 2/3 WL Cox, is associated with the gate to source. Okay, so if you remember, CGS is approximately equal to 2/3 Cox W times L for a SAT device. So the approximation I have done over here is I have ignored the overlap capacitance, because overlap is a very tiny overlap. So then in that case, our transit frequency is going to look like 2 pi Ft, which is equal to, so the numerator represents Gm, the denominator represents the CGS value. We ignored the CGD value because that is very small. It's only the overlap capacitance between gate and drain. And CGS will have overlap capacitance plus 2/3 Cox W times L. Here also we ignored the overlap capacitance, and this is the equation. So now we can cancel out W, cancel out Cox, and omega t will be equal to 3 divided by 2 mu n divided by L square VGS minus VTH for the transistor. So the key point I want to make here is, over a period of years, as the CMOS technology has improved, what is the most important feature that has improved? It's the channel length. So when we say a device is when I'm working in a 2.5 micron technology. For example, when I was in IIT, I was working with a 5 micron technology for my BTech project. So from 5 micron technology in 1989 to now, we are somewhere at in nanometer range. Our recent chip was 65 nanometer. The next chip we are going to work on is 40 nanometer or 20 nanometer, 28 nanometer technology. So when I talk about these numbers, I'm actually talking about the channel length of the device, minimum channel length. And you can immediately see here that the omega t value, we will get larger and larger value as the channel length starts dropping. And we have a square factor, which even makes it great for us. So as length decreases, omega t increases substantially as a squaring function due to squaring function here in this calculation. Let's take a quick example before we close. So for example, ft will be equal to 3 divided by 2. Again, here I'm talking about hertz, and here omega t I'm talking about radians per second. So there is 2 pi, that factor that we have to take into account. So let's take an example of a recent process. L square. So 3 divided by 2. Mu n is 400 cm square per volts second divided by, let's say, 65 nanometer technology. So that would be 65 nanometers square multiplied by, let's say I choose my VD sat or VGS minus VTH equal to 100 millivolts divided by 2 pi. So if you take care of all the units, you will see that this FT value comes out to be 226 gigahertz. So we can use 65 nanometer technology. Beyond 226 gigahertz, the transistor will not be worthwhile. But below 226 gigahertz, it will work fairly well. And we don't try to operate close to 226 gigahertz, but we should be able to operate this transistor at 100 gigahertz or low range. Okay.